Welcome everybody to the lecture number 9 in our microwave engineering course. This lecture will be talking about an important topic, which is impedance matching. So the idea of impedance matching is illustrated here, where we have like our load, and here we have our source or signal generator, and there is a mismatch between the signal generator and the load. So we insert some sort of like a network in between the two of them so that the load will be matched to the source. So why do we need impedance matching? Like there is many reasons for using impedance matching. For example, maximizing the power delivered to the load. So if we have a source that's matched to the line and we need to maximize the power delivered to the load, we need to have like impedance matching. Impedance matching also is very useful in like minimizing the number of round trip, and for transient like behavior it would be desired, and also in some cases it improves the signal to noise ratio. Also, like it's needed to reduce the amplitude and phase error in some like power distribution network. So in general, it's needed for many applications for microwave circuits. And in general, as far as the load impedance is having a positive real part, we can find a matching network. So the question would arise, is there a negative real part? Is there a negative resistance? So in reality, physically there is no negative resistance, but some component or some circuits can behave such that there is a negative impedance. So it's the behavior, the collective behavior looks like a negative impedance. But negative impedance as is, negative resistance doesn't physically exist, but equivalently there is some conditions for this to happen. Okay, so let us say what are the main conditions or like main attributes to say this is a good matching or not a good matching. So there is a number of factors that affects like the use of a matching network. For example, complexity. So like simple matching network is usually needed or desired. It would be cheaper, it would be smaller, it would be like more reliable, less component. So in general, like less complex design is always desired. Bandwidth. So in general, when you are using microwave networks like or circuits, so that we like send signal or receive signal or process something, and signal means there is a bandwidth, and when like our signal is working with like certain bandwidths, we need the matching also to be working across this bandwidth. So we might have like a matching at a single point in frequency, but it is desired to be like across the whole operating band, frequency band of the network, or like the circuit or the application. So the bandwidth of the matching network is something also important. Like implementation, we might have like a very nice design for like a matching network, but when we come to implementation, it's very difficult, it's complex. For example, like think about like matching like a coaxial cable versus matching a microstrip line. So matching a microstrip line or like putting a matching network for a microstrip line is something simple and easy. Putting a matching network for a coaxial cable or for a rectangular waveguide is something complex and bulky, and it does have like multiple consideration. Also, adjustability. So is this matching network like a fixed value, or there is some tuning? Because like when sometimes you need tuning, for example, like if you manufacture something like from one batch or from one part to the other, there is a small variation. So if your matching network is fixed but the load is variable, the matching quality will be not that good. But if you can have like some tuning into your matching network, then this adds up to the goodness or the quality of your matching network choice. So those are some would like to say qualitative issues or qualitative factors to judge the quality or the suitableness of a matching network. So now, like after this introduction about the usefulness and the factors to like describe the quality of a matching network, we'll start to talk about a number of topologies for matching network. We're gonna start by the simplest one, which is a lumped element matching network. It's called the L network. Why it's called L network? Because it looks like a flipped L, like upside down L or upside down L. It is composed of two reactive components arranged this way or arranged that way. And when we like describe the matching network, we're gonna use Smith chart extensively. Why? Because as we said, when we studied the Smith chart, it gives us a lot of insight inside the problem, the physics of the problem, like in contrary to the analytical solution. Of course, analytical solution for matching network problem exists, but again, the Smith chart is giving us some sort of visualization for this. So the idea here, like of using Smith chart, gonna show the benefit and value, and also it can like arrange your thoughts in a methodological way. So anyway, so this L network does have these two different configuration, either like series and then shunt, or shunt followed by series. And this first style fits the case where ZL is inside the circle of 1 plus JX. So what is this circle of 1 plus JX on Smith chart? It is the circle of one real part. One real part means the real part of the load equals the characteristic impedance of the transmission line, because we know that on the Smith chart the impedance is the relative impedance. That's why it's small letter. So this is the circle of real part equal 1. So this is the circle of real part equal 3. This is the circle of real part equal 0, so on and so forth. So here we're talking about the network is inside this circle. So it is the network does have a real part that's greater than or equal 1. The relative load impedance is equal to or greater than 1. So we use series then shunt. If the load is outside this circle, it means that the real part of the relative impedance, relative load impedance, is less than or equal to 1. So outside here we have type 2, which is shunt series. Inside here we have the first type, which is series shunt. Okay, so this matching network is feasible at lower frequency, up to like 1 gigahertz or like 2 or 3 gigahertz at most. So like the idea here for lumped element is not that desirable at higher frequency, because at higher frequency we know the dimension of the component, the lumped component, the inductor or capacitor, would be comparable to the wavelength, and it will not act as a lumped element anymore. It will be a distributed element, as we described before. So when we go for higher frequency, our matching network is more distributed element rather than lumped element. So the analytical solution, as we said, exists, but the Smith chart solution is giving more insight, and also it arranged our thought in a good way. So like it makes like your thinking more procedural than the analytical method, especially in the like for people like who studied or like are studying microwave engineering for the first time. So let us practice this, like the solution steps, using this example. So it is required to design an L section matching network to match RC load. So we have a load that equal 200 minus J100 ohm to 100 ohm transmission line, and the frequency is 500 megahertz. So Z naught is 100, ZL is 200 minus J100, and we are requested to use an L section. Okay, so first we're gonna okay, before we continue, I would like everyone to review Smith chart, because as I said, we're going to use Smith chart very extensively in this topic. So anyway, first we find the relative impedance, small letter for relative impedance, which is 2 minus J. On Smith chart, 2 would be like this circle, minus J is this arc, so the intersection is ZL. Once we draw ZL, we can draw this circle with the center at the center of Smith chart, and this is constant reflection coefficient circle, which is the locus or the location for any point along the transmission line. So here, because 2 is in which part? It is in this part. 2 is inside here, so we're going to use first line, or like first type, sorry. So like 2, so it is inside this circle, so we're going to use first type for matching. So for first type, like we have a load, then shunt with the load is our shunt element. So when we are dealing with two elements in parallel, it's better to use the admittance, so it will be like a simple addition. Anyway, let us see the steps. Once we have our load defined on the Smith chart, we can flip to use Smith chart as Y Smith chart, as admittance Smith chart. How to do this is just like do a reflection, 180-degree reflection for the load point. So if this ZL, then this would be YL. And now we can think about like this Smith chart as being the admittance Smith chart. So now we are here, and the idea here is that those two elements are in parallel, and this element here is in series. We know that Z naught is real. So the idea here is to have like the combination of the load plus the matching network to equal Z naught. So the input impedance at this point, we need it to equal Z naught. So how would we do this? So the first part is, okay, the idea here is to have like the effect of those two elements together. When we like combine those two elements together, which will be YL plus J beta, we need the total to be on the circle of, again, 1 plus Jx, Z of this value to be on the circle of 1 plus Jx. Why? Because after, if the Z of those two elements together is 1 plus Jx, then we're going to add this element which is minus Jx. So the two, and this is like z, so it would be just adding. So jx plus 1 minus jx, the total would be equal 1, which is a matched for z naught. So in this method, or in this lecture, we'll move from y Smith chart to z Smith chart, like back and forth. So the idea here, we are here on YL, and we need to add an element. It's a shunt element, which means like the real part is untouched. It's a shunt reactive element. It's J. So it's a shunt reactive element. So when we add YL plus this load, the real part would be the same. Real part would be like this circle. This circle is constant real part for admittance, because now we are dealing with this Smith chart as an admittance Smith chart. So adding any element which is reactive, it would be like moving on this circle here. So how much we need to move? So we're gonna move just to reach an intersection with this circle. This circle is the locus for 1 plus jx, z equal 1 plus jx. So this is the circle of 1 plus jx when we deal with z impedance, z Smith chart. So if we want to map this circle to the y Smith chart, it would be the mirror. You can do it like each point you want to flip this point from z to y, you go 180. This point you go 180. You will find out that the equivalent or the map of this 1 plus jx, z equal 1 plus jx on z Smith chart would be like mirrored to a circle here for the y Smith chart. Okay, so the locus for the z equal 1 plus jx is this circle, and we want to move from our YL here to YL plus JB, such that the total of those two shunt elements equal 1, the Z of those two shunt elements equal 1 plus JX. So we need to go at this point. We can calculate how much is this value. So it was 0.2. How much is this value? It's 0.5. So we moved 0.3, and it is in positive. So it's a plus 0.3 J. So this element now is 0.3 J. So B equal 0.3. So now we are here. So Y would be 0.4, same real part, plus 0.5 to this point. Okay, so now we need to do the addition of Jx plus the equivalent load of those. So it's a series. Jx with these two are in series. So we need to convert the equivalent of this back to z. So this value we convert it back to z. So this is the z input looking from this point. Okay, now this z input would move on the same resistance because this is reactive. So the real part will be unchanged. What is the real part here? It's 1 plus something, because this circle is 1 plus something. So the z of those two shunt element would be on the 1 plus something. So we are here. So this is the input impedance at this point, and we want the input impedance from this point to equal 1. So we need Jx to take us from this point to the center, which is the match. Okay, what is the value here? So we have this one here, it's minus 1.2. So we need Z to equal 1.2. So if we have x equal 1.2 and b equal 0.3, we have like an L network matching for this ZL. And as a comparison, when we do like this using analytical solution, you will find that b is equal 0.29 and x equal 1.22. Of course, the analytical solution is more accurate, but as I said, the Smith chart solution is giving us insight. It's making like sense for the procedures that we are following. You can think on a Smith chart and like make the calculation using analytical method. So Smith chart is very good for visualizing, or as I said, like arranging your thinking procedure, because you can draw and say, okay, now I'm here, I have certain load impedance. After adding the first element, I want the input impedance at this point to equal 1 plus some J value. Okay, this is two elements in parallel, so it's better to be done on admittance. That's why we convert from Z to Y. We add those two elements together on Y. The conditions that we want, something equal, Z equal 1 plus something. So it must be a place here on this circle, which is the map for this circle. Once we have the total shunt admittance, we're going to convert it to the input impedance for the two shunt elements connected together. It will be this point. Now I would like to add this reactive component in series to this point to bring me to the matching point. And why do we use reactive component? Because matching network is required to be lossless, so it doesn't like absorb energy or like consume energy from the power on the microwave network. So now we have this solution for X, the series element, B, the shunt element. One other thing that you can think of is that we can have another solution. Moving from here to here, we can think also of moving on this circle to this point. We can come, this is 0.4, so so this is 0.4. It would be this point. So on the same 0.4, this is point. So anyway, this is 0.4, and instead of moving from here to here on 0.4, we can move down to this point. So this point also is on the real part equal 0.4. So instead of going for the B element that way with a positive value, we can go here with a negative value. So when the admittance is negative, we know that it is inductance. When the admittance is positive, we know it is capacitive. So we have this solution that we discussed here, but we also have another solution. So the first solution that we discussed is some capacitance here and some inductance here. We can have the opposite. So this is the solution that we done first, capacitance and inductance. Or we can go from this point. So the first element would be inductance, and if we complete the calculation, the second element would be capacitance. Where this value like C and L came from? It's calculated at 500 megahertz. So at 500 megahertz, the reflection coefficient is 0. So we have ideal match. When we go for like different frequencies than the center frequency, each solution would have a different behavior, and from this behavior we can define the bandwidth. For example, I would say the bandwidth is when we have the reflection coefficient less than 0.2. So we can just do this, okay? Less than 0.2, we can, okay? So for solution number 2, we can have, like, this is the bandwidth. For solution number 1, this is the bandwidth. So this is how we define the bandwidth. It depends on our definition. The bandwidth we must tell more informations. For example, the bandwidth for reflection coefficient less than or equal 0.2. If we go for, like, for example, we can go, okay, like I would like to define the bandwidth as the bandwidth for reflection coefficient equal to or less than 0.1. So we'll go this far, so on and so forth. So this is a bandwidth and this is a bandwidth depending on the definition that we would take. Also, for your information, like, there is multiple different ways to realize microwave L, C, and R. So for example, here we can, like, this is a capacitor, we can put like a planar resistor, we can put like lossy film, we can make an inductor, So there is multiple different ways to implement R, L, and C on microwave circuits. Now we're going to move to another type of matching network, which is called single stop tuning. So stop is meaning some sort of like a leftover, length or something. So this is the load and this is the stop. It's like a part of a transmission line, and this stop can be like ended with open circuit or short circuit. So if it's open circuit, it's called open circuit stop or open stop. If it's short circuited, it would be called like short stop or short circuit stop. So this is our load impedance or load admittance, and we want to add this matching network which starts here and end up here. It includes this stop, such that the input impedance seen from this point equal the characteristic impedance. So we want load plus matching network together to equal the characteristic impedance. So this setup here is called like shunt stop, because the stop, this is the stop, is shunted to the main transmission line circuit. This setup here is called series stop. Why? Because the stop is connected in series to the transmission line. The two design parameters, there is actually three design parameters here. What is the termination of the stop? Short or open circuit. What is the length of the stop? And what is the distance between the stop and the load? So we have three design parameters: the termination type of the transmission, the stop, the termination type of the stop, length of the stop, distance between the load and the stop. Those are the three parameters. And some like cases or like some real circuits, the shunt would be easier. For some other circuits, the series would be easier. It depends on the kind of transmission line or waveguides that we are dealing with. Again, we're going to use Smith's chart extensively here. The same idea, we are trying to solve a quiz. So we have like some quiz and we would like to solve. The quiz is that, okay, given load L and characteristic impedance Z0, what are the setup for, how can you find D and L for like this kind of stub or this kind of stub, shorted or open, so on and so forth. So let us see how would we solve this problem. So the idea here, okay, so we have YL here or ZL here. When we move certain distance, we will come to this point. At this point, we want the input admittance to equal 1 plus J something. Why? So that when it's added to this like shunt stub, the total would be 1 plus J plus the admittance of this part. The admittance of this part is always reactive. The shunt is always reactive. The input impedance of this stub is always reactive. So at this point, we want the inductance to equal 1, the relative inductance at this point before the stub, to equal 1 plus certain admittance, J something. Then we can choose L such that its admittance is the opposite of the imaginary part. When we add them together, the input admittance here and the input admittance here, the total would be 1, so we have matching. Here we think with like impedance in mind. We have ZL, we need to move certain distance such that the input impedance at this point equal 1 plus Jx. Then we add this part which does have an impedance equal minus Jx. When we add this section to this section, they are in series, the total would be 1 plus Jx minus Jx. So Z input at this point would equal 1. So this is how we think. This is how we search for the solution. Okay, let us practice this with an example. The example here is for a shunt stub. It's giving us the load, giving us the transmission line, giving us the center frequency, and would like to find like the matching network for this, and it's telling us the stub is short circuit. The stub is short circuited shunt. Okay, so let me copy the shape for shunt single stub. Okay, just to be like visualized in a better way, I brought like this network here. So we have ZL, but because of that it is shunt, we need to move to admittance. So we can put Z load, this is the relative load impedance, which is ZL is here. So we'll take ZL at this point. We're going to draw the constant reflection coefficient circle. So on the transmission line here, for this section, any point would exist on this, like any point here is equivalent to a point on this constant reflection coefficient circle. So we are here, and we are in this direction, we are moving towards generator. In that direction, we are moving towards load, and this is moving towards generator direction. So we are here, okay? So this is the impedance, but as we are dealing with shunt, we need to deal with admittance. So YL would be here. So we are at this point, and we want to move certain distance towards generator such that the total input, or like the input admittance, equal 1 plus Jx. So we are here, we're going to move to 1 plus Jx. So it's something on this 1 plus Jx circle. So we can move from this point to that point, or we can move from this point on the constant reflection coefficient circle to this point. So this is bringing us a solution. This is bringing us another solution. We can move this distance, so the position of the stop is D1 away from the load, or D2. What is the value of D1? We can read here the value and move to this point and find the value. So for the D1, we can read here from this point, it's 0.176, and this point is 0.065, so 0.06, 0.65 down to 0.176. So we can find the value for D1, and we can find the value for D2, which is going to 0.325. So either we go for 0.11 lambda to this point, or going to 0.26 lambda to this point. Okay, so now at this point where we're going to put the stop is at this point or that point. So how much admittance do we need from the stop? We need from the stop the negative of this admittance. So if this admittance is 1.45, so we need an admittance of minus 1.5 from this short circuit stop, so that the total would bring us to this point. Okay, so y1 equal 1 plus 1.47, y2 equal 1 minus 1.47. So for the first solution, we need the short circuit stop to have an admittance of minus 1.47. For the second solution, we want the admittance of the stop to equal plus 1.47. Okay, so for a short circuit now on the same graph, we can put like the short circuit is at this point. So now short circuit impedance is 0, which is the outer circle on the Smith chart. So we want this to give us 0.147 admittance. Okay, so we want, like for first solution, we want the admittance to equal minus 1.47. We are from this point, this is at the short circuit, and we need to go for 1.47 with negative, so it takes us up to here. So at this length, which is 0.34 something, we need the length of the stop. For the second solution, we need it positive, so we'll move from here, from the short circuit towards, so the short circuit is at the load, and we are moving towards generator, which is the input of the stop, and we need the value to be 1.47, which is at this point, so this is the length L2. So the solution for first solution, we are that length away from the load, and we want this stop, the length of this stop is 0.095 lambda. This is solution number 1, and again this is short circuit. For solution number 2, this is how far we go from the load, and this is the length of the stub. So we have those two solutions. For solution 1, we are here. I think there is some mismatch. Okay, sorry for that. Okay, so now to calculate the length of the stub, we're going to start from the short circuit. Short circuit for admittance would be this point. Short circuit for impedance would be this point. So we're going to start from this point and move to like admittance of minus 1.47 for solution number 1, which is this length. So this length is less than 0.1. We are starting from here. You will find it's 0.095. For the second solution, we move to admittance equal 1.47. So we go from this point all the way to this L2, which is 0.405, something like that. So those are the two solutions. And here, this is the behavior of the two possible solutions, solution 1 and solution 2, as a function of frequency with a best or like perfect matching at the center frequency of 2. Depending on the definition of bandwidths, we can find the value. Okay, another example on single stub matching for series stub, and this series stub is open circuit. It's giving us the load and the impedance as well as the center frequency or the frequency of interest. We're going to do something very similar. Okay, let me again also like copy the solution. Okay, so now we're going to move to like another style of matching, which is the double stub matching. So for single stub matching, the separation between the match or the stub and the load is a variable. Sometimes there is a constraint. We can't put the matching network anywhere. So sometimes we have access to the circuit at a specific position. So the separation or the distance from the load is not a variable for us. So how would we do a matching under this constraint? The idea is solved by this double stub matching. So the double stub matching can go in a specific, so you specify certain distance from the load and you put your double stub matching. The double stub matching is like two stubs with like a separation in between. The length of stub 1, the length of stub 2, the separation between the two stubs are design parameters. The stubs can be open circuit or short circuit. They can be mixed. One is open, other is short. So it can be many different combinations. Okay, so this matching can match any load. Since we are at a specific distance from the load, so we have some sort of like input impedance here that we can match. So if we can solve the problem with the double stub matching, is first stub is at the load, now we can solve any general problem, because if we want to put the double stub here, so we're gonna assume YL is the input impedance at this point. So solving this problem is general, even though it's a special, or like it's like we are putting the stub at the load. But again, if this is the case, there is a distance between the double stub and the load. So the load that we're going to match will not be this load. It will be the input impedance at this point. Okay, so this is the problem that we solve. It is general, because this problem can be reduced to this one. If we can solve this one, we can solve any general problem. So the idea here to solve the problem, so at point 1, we want the input impedance to equal 1 plus JB. So Y stop 2 would equal minus JB. Okay, so the problem is solved like this. From here, this is at point 2, we want the input impedance at this point, looking here, to equal 1 plus JB. Then we choose JB2 to be the negative of that. So the total input admittance would equal 1 at this point. So here we have, okay, let me do it, this would be clearer. Okay, so the idea is that the input impedance at this point, looking into this direction, would be equal 1 plus JB. Then at this point, just after the second stop, the input impedance would be 1. So it's matched. So at this point, we know that we need the input admittance to equal 1 plus JB. And at this point, we know the admittance, it's YL plus JB1. So 1 plus JB is like the circle of 1 plus JB, which is this circle. So we're going to take this circle and rotate it by moving towards the load. So we're going to move like counterclockwise. So we are taking the locus of this point, 1 plus JB, and move it certain distance D. So we're going to rotate the circle. Rotating the circle is just rotating its, we are rotating its center with this distance towards the load. This would be the locus at this point. Then we have YL plus JB1 is another locus. The intersection between the two locus is defining B1, and later on we define B2, as we're going to see shortly now. So okay, so now first step is stop number 1, which is B1. We're going to move the load admittance to Y1. So this is, okay, so the idea for the double stop matching is we first define YL. So YL will be located on this circle here. This circle here is a circle of constant real value for YL. Okay, so YL with B1 should be like the same real part, but it's just moving on to a different imaginary part. So at this point we are located on this circle as well. Okay, so now from here, let me bring this. Okay, so here this is YL. So the blue curve, so at the blue, the input admittance at this blue point after the first stop would be located on this circle of constant real part. Okay, now looking at this point here, just before the second stop, we need the input impedance to be 1 plus Jx. So the locus for 1 plus Jx is this circle here. Sorry about that. And now we're going to take this circle and rotate it towards load. So the locus at this point, at the red arrow, is here, and this locus at the blue curve would be just rotating this circle d distance towards load. So this would be the locus of the input admittance at the blue arrow. The two intersections here and here are the two possible solutions to find JB1. So the intersection between this constant impedance circle and the locus of this 1 plus JB rotated is Y1 and Y2 that defines the needed admittance of the first one. So the first one, this is YL. If we moved with this much admittance, this would be first solution. From this point to this point, same real part, the difference is B1. Or from this point to this point, the difference is B1. So solution B1 is positive admittance and B1 prime is negative admittance. So this is the position at here, the blue arrow. Then we can take this circle here and, we take this point and return it back to Y2. So this would be the input admittance at this point. We can do the same for this point. We return it back and we are here at this point. So it's just like a rotation from here to here, or from this point to this point. And the rotation here would be just from the center to this curve, or from the center over this curve. So this is Y2, which is the input admittance for solution 1. This is Y2 prime, the input admittance for second solution. Y2 prime here, we need to have the second stop to be the negative of this value or the negative of this value, so that it brings us to the origin. Either take us from this point to the origin or from this point to the origin. Okay, so here we are adding positive admittance, here we are adding negative admittance. So B2 and B2 prime. An example to illustrate this. So we need to design a double stop shunt tuner. So shunt load impedance is ZL given 50 ohm transmission line. The stops are open circuited, separated by lambda by 8. So it's giving us all the needed information. It's giving us the tuning frequency, giving us the range that we need to study the behavior over frequency. Okay, so ZL would be, ZL is 60 plus J80 over 50, so it's 1.2 minus J1.6. It would be so YL would be at this point 0.3 plus 0.J4. So you can first find ZL at 1.2 minus 1.6, and from Z2 you can find ZL. So the locus of first stop would be on this constant admittance circle, the circle of 0.3, this circle, and the other locus is the shift of this 1 plus J curve with a distance D, 0.8, towards the load. So counterclockwise. So this is the locus of another locus for y load plus b1. So the two intersections here are this one, y1, and this is y1 prime. Then we took those y1 to the y2, y1 prime to y2 prime. So we can find the solution for b1, which is this value. It would be, it took us from here to here, so it's 1.34. Like b1 prime, it's from here to here, which is negative 0.114. So for y2, which is from here to this point, it's equal 1 minus 3.38, or y2 equal okay. So this is solution 1, this is solution 2. So for solution 1, we want the second stop to be the negative, so it's positive 3.38, and second solution minus 1.38. And from this value we can find the length of the open circuited. This is inductance, so open circuit inductance would be at this point, so L1 would equal 3.8, so it's 1.4. This is, and L2 equal 0.24. So we have the solution here. So the idea here, we need B2, which is open circuit for Y, open circuit shunt is here, and we want to move like to 3.38, which is, this is 2, this is 3, 3.38 is somewhere here, so it's L2 equal 0.204. Y1 we like did before, 0.146 from this point to this point, so we go from 0.4 almost to 1.8, so it's 1.4, so on and so forth. So this way you can like solve the problem. It's requiring you to understand the sequence, the motions, what are, like this curve is like a curve on a circle centered at the origin. From origin to this point we move till we intersect here. From origin to this point we move till we intersect here, and we come up with two solutions. And once we have the solutions, we can draw its behavior over frequency. Lambda by 4 transformer is another type, which is a simple circuit for matching, and we had done this the drawback or disadvantage of this solution is that it can only match a real load. For complex load impedance, transform it into a real one. We can use like an appropriate length of a transmission line. So if this is imaginary or like complex, we can move certain distance on the transmission line to make it real. Once it's real, we can add our lambda by 4 transformer, and that is the end of this lecture. Again, you need to watch especially the double stop matching. You need to read it, study it, try it out to understand the too many circles that we draw for the intersections, but the story like is clear. You can understand it, and we have like a homework in a week from our discussion session. Thanks everybody, and meet you in the discussion session.